Okay, in this case, we are going to attempt some questions that are related to electric forces. This is the first question where we have a small object that is carrying a charge of -8 nanocoulomb, and there is a downward force acting on the object, and the magnitude of the downward force is 20 newton when placed at a certain point in the electric field. Okay. The question is, what are the magnitude and direction of the electric field at the point in question? So we assume that there is a field, we have an electric field somewhere here, and this is the point where the object is placed. And here we experience a downward force of 20 nanonewton. And we place our charge here -8 nanocoulomb. Okay, so there is a field here which creates a downward force on our. So let's draw a line to represent the field. This is trying to tell us the field, but we don't know the direction. Our next task is to find the direction of the field. So the word downward, we take care of the word downward. The fact that our force is acting downward. This force is going to be given by the charge times the electric field, where our charge is this charge and this E is our electric field. So if this force is downward, it means our electric field, if this were positive, if here were positive, then our electric field should be such that the force is facing downward, that is pulling this down. But for us to have an attractive force that will pull our negative charge down, definitely our field is supposed to point upward, because the attractive force here means that the source of our field is a positive charge, and the positive charge, the field from positive charge is going to be away from it. So this is telling us that our electric field is upward. Then now let's evaluate the magnitude of our electric field using this relation. This is the force over the charge. So our force is 20 times 10 to the power -9 nanonewton over our charge, which is 8 times 10 to the power -92. So this will give us 2.5 newton per coulomb. This is our magnitude of the electric field, and the direction of our electric field is upward, meaning that the source of the electric field here has a force is positive, and this part will now create an attractive force between the positive charge down here and the negative charge. So since we have an attractive force which is pulling this down, then our field is going to act upward. So this is part A. The magnitude is 2.5 newton per coulomb. The direction is upward. Now let's look at B part. The B part is this is the part of A. Okay. Now the B part is the question is, what will be the magnitude and direction of the force acting on a proton? So now we put proton in this place. So already we have identified that our field is upward, and the magnitude of the field is 2.5 newton per coulomb. Then if we place a proton here, we put a proton here, positive E, then this field will act on this positive charge, that is the proton, and in this case our force is going to be repulsive. Our force is going to be repulsive, and again our force is going to be upward. Okay, in this case, because it's repulsive, there is a repulsive force upward here, so the force is going to be upward. And the magnitude of the force is now going to be obtained from the Q multiplied by the electric field, which is 1.6 times 10 to the power minus 19 times our 2.5. This will give us a total force of 4 times 10 to the power minus 19 Newton. So this is the force, the magnitude of the force, and it is upward also. In this case, it's also force is upward. Okay, this is the direction. Okay, here is a second question. In this case, we are to find the distance between 2 point charges. This charge 1 has a magnitude of 26 microcoulomb, and charge 2 has a magnitude of 47 microcoulomb, so that the force between them is 5.7 Newton. We can easily see that since Q1 is positive and Q2 is negative, this force is an attractive force. So we can place our charges here. This is our Q1 and this is our Q2, and since one is positive and another one is negative, there is an attractive force F, which is given by 5.7 Newton. Okay, from our relation of the Coulombic force, our force is given by the Q1, Q2 over 4 pi epsilon naught r square, where r is the spacing, the distance between the two charges. So in this case, our concern is to find r. So we can make r the subject of the formula by cross multiplying to have r squared to be equals to Q1, Q2. We'll turn f down here, so it's 4 pi epsilon naught. So we can now insert our values to evaluate for the our Q1 is 26 times 10 to the power minus 6 times Q2 is 47 times 10 to the power minus 6. Okay, all over our force, which is 57 or 5.7 times our 4 pi epsilon naught. So 4 pi times 8.85 times 10 to the power minus 12. When we evaluate this, we are going to get a value of 0.518 meter square, which will now give us r by taking square root of this to be around 0.72 meter. So this is the distance between the two charges of this magnitude, 26 microcoulomb, 47, where the force of 5.7 can exist between them. Okay.